Now we are officially recording. Good evening, everyone. So before we get started, I wanted to just update you on our week material and see here on Canvas. You notice that we are 1 week behind. We're covering tonight basic methods for causal inference, and next week we're going to be talking about instrumental variables and two-stage least squares, right? So in terms of the midterm, this is going to include weeks 1 all the way to 5. I got some questions before the class started. So week 1 all the way to 5, including week 5, is on the midterm, but not status skills. And what I'm going to do is, for us to be able to get back on schedule, what I'm going to do is to record a session on status skills. And again, this is just something extra. You don't need to know status skills for the midterm or even for the project. Those are additional commands that you can have on Stata, and also some tips on how to construct tables using Stata, so therefore your presentation skills can improve with those. So I'm going to be recording the week 6 session, and I will be uploading those on Canvas. So when we are back from the midterm, we're able to continue on our schedule, okay? And also you can ask questions, and I can hold individual Zoom sessions anytime. So please feel free to reach me if you need to do that. Tonight, we're going to cover the material on chapter 7. And I don't know if you had a chance to take a look at this, but this is a miscellaneous chapter that includes many different things. But I think an overarching theme for this chapter is really how can we bend some assumptions, how can we twist some of the assumptions we talked about last week and still be a little bit okay with them when it comes to making causal inferences and active predictions. So we're going to focus on some of those assumptions and see how can we modify them or adapt them or be okay with them as we move along. So last week we discussed 4 or 5 assumptions. So we talked about linearity, random sampling, we talked about exogeneity, and also homoscedasticity. So we said that, you know, having all those 1 to 4 assumptions being valid will therefore guarantee that we would have good guesses, that our parameters would be good guesses of the populational parameters that we care. Now, what happens if we break some of these assumptions? So we're going to be focusing first on assumptions 2 and 3. The reason that is because they quickly align to the idea of experimental design, so random participation and random selection. And then we're also going to touch on assumption number 1, which is a little bit more benign. We're not going to talk a lot on about assumption 4, because assumption 4 can be easily fixed with a command that I will talk about. So that's the goal for tonight. So putting together all these different things. So let's start talking about assumption number 2. Okay, so the chapter initiates really discussing what happens when, for some reason, we don't have a random sample anymore, right? So what will be an instance in which we wouldn't have a random sample? Let's say you care about a certain population. So let's see, you care about, you know, understanding how young adults behave according to purchasing behavior of your product, or you care about having enough Brazilians in your sample. I don't know why, but maybe you care about having enough Brazilians in your sample to be able to make inferences about them. So in some cases, it's not guaranteed that when you have a random sample, you're going to be left with a sample that you really care, according to some categories that you really care about, such as age or demographics that you care about. So you would like to be able to have a sample that have enough of the people that you care about to be able to then make hypothesis testing and all those things that we discussed. So whenever this is the case, we go from a random sample to something that we call selected sample. Selected according to some categories that you care, that you are interested in analyzing. You must have enough of those people to be able to then conclude something about them. So there are basically two ways in which we can have a selected sample. And by selecting the sample, of course, this sample is not random anymore, right? Because it has more Chinese or more Brazilians than what a random selection would pick up. So we can have two types of selections. We can have a truncation or a selection in the X variables, in your independent variables, and we can also truncate the sample along the Y dependent variable. What are the consequences of doing so? Are we going to be still left with consistent estimates? So that's something we care, right? So let's imagine that we truncate the sample first by your X variable, by selecting according to age in this example that you have in front of you. So I'm selecting here my sample and I'm truncating. So here the blue line is cutting the sample, and I'm only able to, and I'll, in such a way that I will have individuals that are younger or equal to 30 years of age, right? So for some reason, I want to study these individuals more and I want to learn about them. Is this a problem in terms of consistency? That's not going to be a problem for you. So truncating the sample in your X variable is usually not consequential. The reason why this is true is that you can still see the relationship. You can still see the regression line well if you do that. Even if you have a limited part of the whole sample, you can still trace your regression line. So basically all those reasoning box, assumptions 1 through 4 will still apply here, and in such a way that you're able to carry on with your analysis. Let's say for some reason, you know, you want to just consider the working population, right? So it's very frequent to exclude people in mental facilities, hospitals, prisons, children, retired. So excluding a whole category, excluding a whole population here will not be a problem, unless, of course, you want to make inferences about the excluded group. So selecting in the X is perfectly fine.
I have a question, Professor.
Mm-hmm.
And is this true? You know, this has a linear relationship, but if we truncate it in a way where it was not linear, then would that still hold, or is that a different, like, that doesn't apply? Mm-hmm. This applies only to linear and doesn't apply to non-linear.
Yes, that's a very good point. So there is a drawback from doing so. So you want that relationship to be as more stable as possibly, right? So if you for some reason you worry that people below 30 are completely different than people above 30, they behave in very different ways. So you see a big jump and you see a big and you have this big non-linearity that you're considering, then of course making inferences and predicting something about this population over 40, over 30 would be problematic, right? So here we're implicitly assuming that, you know, this jump is not very strong, that this relationship is smoother. Okay, so, but extrapolation would be a problem. If you are going to extrapolate and those two parts are completely mismatched, therefore you would have consequences.
Okay.
Now, let's take a look at a deeper problem. Something that is not a good idea and that is going to be a problem is selection by your Y, your dependent variable. So here we have an example in which we're only able to observe, we're only interested in truncating the sample for which rating is above 60, right? So what that causes is, you know, in black, we're able to see our regression line and you have our scatter plot. But in green line, the green line is the truncating line. So we're only going to be looking at the data points above the green line. Now let's see why this is going to be a problem, okay? So let's just, if you can just put your hand on the top of the green line and observe the data points only above the green line, what do you notice about the residuals? What do you see about the error? So there's going to be two things, right? So we're going to have, in the beginning of the distribution, we're going to have a predominance of positive error terms. What is an error term? The difference between each point and the estimated regression, right? So basically we're going to have positive errors in the beginning of the distribution, and at the end of the distribution we're going to have this error term being more balanced up and down. So our mistakes, they balance out at the end of the distribution, where my truncation is not going to matter so much. But really at the beginning, I'm going to have a predominance of positive error terms, right? So if that is the case, then you want to think about the assumption of exogeneity that tells us that on average, the residuals should be 0. This is not going to be the case here anymore, because I'm going to have positive errors and then zero errors more at the end of the distribution. So the mean of your error term is now positive. That's a problem. And the second problem is that now we have a correlation between the error term and your X variable age. So when my age is higher for individuals that are 60 years old, my error term is going to be balanced out. It's going to be approximating 0, but at the beginning, I'm going to have a positive error. So the punchline here is that we're violating this very important assumption of exogeneity. We're saying our error terms, they do not have mean 0 anymore, and we do have a correlation between the error term and one of our x's, which here is age. The problem that this creates is that now we're going to have biased estimates. Our betas are not good guesses anymore. We have a problem. We cannot say, hey, this is my estimate of the effect of age on customer rating. Your estimate is basically off. Okay, so truncating on the Y variable, problematic. Truncating on the X variable, not so problematic. This is probably going to be a question in your exam. So that's what you need to remember in terms of the first part, the violation of randomization and therefore selected sample. Okay? Now let's talk about violating the second. So Brad is asking me, would this type of truncation typically be done after creating a model? Well, it's typically done on your sample selection, Brad. So sometimes, I'm just interested in observing, in having a lot more Chinese or Brazilians in my sample. And the way I'm going to select my variables is going to definitely generate these more predominance of those demographics than otherwise. So this is usually something that happens in the process of data selection, of narrowing down the whole data that is available to you. And I can also upload an exercise on how to do that on Stata if you are interested. Okay, so let's move on and talk about the much more important assumption that I want to discuss tonight, which is endogeneity. Thank you. So endogeneity, this is key for this course. If you conclude the course and you are comfortable with this assumption, and if you are able to explain to me in your project that you really understand endogeneity, that's what I'm looking for. That's what the course is looking for. Okay, a really understanding of the consequences of breaking down or violating exogeneity. So let's take a look at this picture first, which you may have seen before or not, I don't know. But we have temperature against pyrites, right? So pyrites are going down in the x-axis and temperature is going up. So one may look at a picture like that and say, pyrites prevented global warming. Of course, this is not true. But if you were to run a regression using X and Y, that's what would come out of it. So what else is going on here? what is the problem of this relationship? Is this just a correlational relationship? Can we use this relationship for active prediction, for causality purposes, right? So how can we investigate and really try to narrow down the problem here? What is going on? So in order to illustrate this problem, I want to bring you to just a reminder of this biggest assumption in the course, which is exogeneity. Exogeneity is basically telling us that you shouldn't have anything in your error term that is correlated with any of your axes. If you have something in your error term that is correlated with your axis, with your treatments, that's a problem for you, right? This is going to be a problem. Why this is a problem? Because as analysts, we want to say, hey, we have these good estimates of effects that we're pursuing, that we're investigating. But if we have endogeneity, this is just basically saying that your estimate is off. You cannot say anything anymore, right? So let's think about how this can happen. And selected sample, if you select it according to your Y variable, this is one reason that generates biased estimates. But a more common reason is due to something that we call omitted variable bias, okay? And to illustrate that problem, I want to go ahead and work with you on a simple regression here, where we're basically trying to estimate a demand curve, okay? So what is a demand curve? The effect of prices on sales. This is a very basic question that, you know, any firm would be interested in answering. How can I change my price and this will impact my sales? I want to understand this mechanism, right? So let's load up the data set. This is called sales DTA. So let's go ahead and hop on Stata, which you guys are very good at. I could see from your homework that you're doing very well. So, and I'll be able to give your grades over the weekend pretty soon. So let's just do a simple regression, sales on prices. Let's press enter. Oh, not prices, but price. It makes a difference. So here we have a coefficient of 2 for price. Let's now run an alternative regression. Let's regress still sales on price, and let's add a third variable called market size. Let's press enter, and what do we get? So let me go back to my slides here. On the one hand, when we run the first regression, and I'm going to teach you on the next video for Stata Skills how to build these nice tables, okay? So this is a table you actually can build on Stata, and I'll go over that just in case you're interested in, you know, having a better presentation. Let me just stop here and also say something. When you want to copy, let's say you want to copy your output into your homework, okay? So you can take a screenshot. That's something you can do, not very, you know, not the best option. But the other option you can do is just simply Control-C. You can copy and you can paste this output. But if you're going to do that, you need to change the font size to Courier New size 8, okay? So if you do that, I think it's double R, I might have misspelled. This is gonna look a lot better, okay, in your homework. So next time, just copy and paste, change the font. It's gonna be looking better than actually just taking the screenshot, in case you wanna.
Manisha, I have a question about that. Real quick, so how important is that for us to copy and paste instead of taking a screenshot? The reason I ask is because when we are on the server, on the IU server, the copy command on the server doesn't translate to the paste command on our desktop. Mm-hmm. So we really cannot copy. I tried and cannot copy and paste anything between the servers and the desktop.
I have other cases in which students were able to copy and paste. I can investigate why that is and get back to you. But if you want to just, you know, take a screenshot. If you cannot, that's fine. And next week, Manish, I'm also going to go over how to build those tables. So this may be an even better option, right? Because it looks a lot more professional. So I can do that. It's not required. You're not going to be taking points out of that, not even in your project, okay? But it's definitely something that makes your presentation a lot better.
Okay, appreciate it. Thank you.
Perfect. So going back to our two regressions, what do we see here? Comparing the two estimates that we have a big swing, right? So we went from a coefficient that was positive to a very big negative coefficient. This is alarming. This is a red flag. This is showing us that endogeneity is likely present in the first model. We see this huge swing, and also having a negative coefficient for a demand estimation makes a lot more sense, right? Why this is happening? When we added, can somebody explain to me why that is? Why do we see this big change?
I think the independent variables are measured with an error.
Mm-hmm. So you're talking about measurement error. Measurement error is a possibility. Measurement error is also something that generates biased estimates. But the biggest culprit here seems to be the omitted variable, right? So what happened when we, simultaneity, somebody's talking about simultaneity. That's something that also generates biased estimates. But the most common thing, the most common way in which endogeneity manifested itself is through a third variable, in that case here, market size, that is being in the error term is affecting our estimates, right? So market size, when we think about the size of markets, probably markets that are bigger, they are, this is going to accompany higher prices. So managers are going to set prices to be higher in bigger markets, say Chicago as compared to Indianapolis. And probably sales are going to be also higher when the market is bigger, right? So there is a correlation here between market size and our treatment price, and also market size and sales. So we have a variable. So when we run the first regression, sales on price, what is happening? Market size is part of the error term, and market size is correlated with price and also sales. Why this is a problem? Well, this is a problem because as analysts, we're trying to answer the very simple question of how prices affect sales, right? So when the analyst runs the first regression, have not taken an econometrics course, just take his sales data and regress on price and say, hey, I have this coefficient of 2, this person will conclude that raising prices will raise sales. That's the conclusion he may get. Well, it turns out that this regression is not causal. This regression is suffering from really a violation of endogeneity, of exogeneity, which is known as endogeneity. We have market size correlated with both price and sales, and what this is causing is that we're going to have basically two effects, right? We're going to have a direct effect, prices affecting sales, but we are also going to have an indirect effect. When price is changing, market size is also changing because they are correlated. And when market size is changing, then sales is also going to be changing. So the problem of having this omitted variable market size in the error term is that we're now changing price and we're changing things in the error term at the same time. So we have this multiple jumbled up effect of many things happening together. So you're not able to tease out just the effect of prices. And what you get is a biased estimate. What you get is an estimate that is completely off, right? So the role of bringing up market size into our estimate is to really help out with this problem. When you are controlling for market size, you're saying, hey, for markets that have the same size, when I change prices, I'm holding this market size constant. And when I change market size, I'm holding price constant. So that's essentially the mechanism through which endogeneity is manifesting, right? Having these variables in the error term being very problematic. Are there indicators? So Brad is asking me, are there indicators to test for endogeneity in only the first regression in a way to identify? So we're going to talk about the Hausman test, Brad, next class, to actually know whether, even taking care and doing some simple measures to see if endogeneity is a concern. But really, it is also a theoretical argument, right? We're going to also talk about the Hausman test, but it's really also an argument of sitting down and thinking, hey, what could be potentially in there that is going to be correlated with price and sales? Now, some of you there are too fast in talking about endogeneity will just tell me in the homework or any assignment, this regression is not causal because we have things in the error term, right? So that's the typical answer I get from many students. Oh, we may have, these characteristics there in the error term, and this will cause endogeneity. It's not a problem for you to have things in the error term. The problem for you is to have things in the error term that are correlated with your treatment. And of course, by definition, being the error term is going to be correlated with your dependent variable. But you must say that those unobservables are correlated with your treatment. And that's what creates endogeneity. Okay?
Professor, I have a question.
Sure.
So, you already had the data on market size here, but what if you didn't have that? Where does it end in knowing that these different variables are affecting the equation, like income or advertising budget? All of those could have an effect on price and sales. So how do you determine which ones need to come in?
I love your question. I really do. And it just brings us this whole idea that econometrics is about mitigation, right? It is not about achieving the best possible model, which, we're always going to have some endogeneity at the end, but it's about how conscientious, what are the steps you took to mitigate that problem as best as you can. So we're going to talk today about simple strategies, and until the course is over, we're going to talk about more advanced techniques. So next week, we're going to talk about a very important technique and a much more advanced technique, which is instrumental variables. But this week, we're going to just take a look at simple measures you can do, right? But I really appreciate it. It's a very good question. So moving on, we already talked about omitted variable, right? Having this variable in your error term that is correlated with both X and Y, and it's jumbling your conclusion, making you unable to tease out. The other way you can think about that is, hey, prices are not randomly assigned, right? Managers, they don't throw a coin and say, here's price going to be high and they're going to be low, high and low. No. So just by construction, right, these managers are thinking about the characteristics of the market, the consumers' characteristics, demand and supply, and things like that. So by construction, estimating a demand function, many students think that is a simple exercise, but this is one of the most complex exercises that can be. Estimating the effect of prices on sales is complicated if you want to do it properly. So this is basically just explaining the direct and indirect effect that we talked about. Remember always this back channel effect of your treatment changing, your error term changing, and you're not able to separate those. So as we have that question just now of how can we proceed, given that we know endogeneity is going to be a problem for us as analysts, right? To be able to state our claims and to be able to quantify effects all the time. So what can we do? It is a matter of degree. It is not a matter of attaining 100%. So a very simple solution that we can think about is to just do what regression number 2 have done. So basically try to identify things in your error term and pull them out, things in your error term that really matter, right? They're relevant for you in solving endogeneity. And really pull them out and really include them in the regression, because once you bring them out and you're including the regression, you're controlling for them. You're making them constant. They're not rolling around in your error term anymore. So the first solution that this chapter is going to talk about is the use of controls. What is going to be a good control? Any variable? No, a variable that really is something that is correlated with both your treatment and also your outcome variable. That variable must be taken out as best as you can and be included. So if you're thinking that market size is going to be correlated with both and you can measure that, go ahead and include it, and other variables, right? So competition measures, things like that, as best as you can, make them controls. Now, as the question that was just asked pointed out smartly, there's going to be a limit to that. There are many variables that you may not able to observe them. You may not able to measure them. How do I measure mindfulness? I just seated in a talk where the person was trying to measure how mindful workers are in the morning when they come to work. What is mindful? How do I quantify this very abstract variable? Well, in that case, we're going to be looking at a proxy variable, right? Something that I cannot directly measure and include as a control, but something that will be very close to what I'm trying to capture. How can I measure stress levels? How can I measure mindfulness? So let's just take a look at, control variables. And a lot of times your controls are going to be things like dummy variables. They're going to be your demographics. They're going to be things that are categorically measured, such as, the state you live, what's your race, what is your marital status, and things like that. Whether this industry is, manufacturing, service, whether this industry is in the south, north, east, or west. So in many instances, your controls are going to be just dummy variables. And these dummy variables, they can be categorical variables, very general categories, or something that has a discernible order to them, like ordinal variables. So you can think about, when you look at a variable, they can reflect degrees of intensity, no schooling, a little bit of education, a lot more, and a lot more, or it can be days of the week. So for those variables, those categorical variables that have a certain order, well, we call them ordinal variables. Now, you probably have seen those variables before and you may work with those before, but I must give you a very important warning. The biggest warning that I can give you when dealing with categorical variables is be careful how you use them and how you interpret them, right? It may be very tempting to just jump at your regression and include the variable the way it is. So let's say you have a variable that is race, okay? And race is going to be 0 if the person is white, for instance. 1 if, let's say, the person is black, and 2 if the person is Native American. Let's put it this way. So those numbers, 0, 1, 2, they have no meaning on themselves, right? They're just allowing me to separate my categories. And if I just regress, wages on race, I may get something completely nonsense. What does that coefficient mean? Increasing race in 1 unit, that's going to impact my wage. That, according to my beta, that doesn't make a lot of sense. You may come to me and say, hey, what about the ordinal variables? Because the ordinal variables, they have a certain level of progression, right? So a little bit of schooling, some schooling, a lot more schooling. So it may be, you may feel inclined to include them in the regression the way they are. But when you do so, you're also going to be careful about what you're assuming. So let me just give you an example of an ordinal variable, right? Let's say you have in your data set a variable that is called market concentration. And that variable is coded 0, 1, 2, 3, 4. So people that have not taken econometrics, they may just use that variable the way it is. They are going to regress whatever sales on market concentration. While it is technically okay for you to do that, you need to understand what is the assumption behind when you are just putting the variable raw. So if you are including market concentration just raw, just the way it comes, 0, 1, 2, 3, 4, what you're basically assuming is that, you know, the effect of going from level 0 to level 1, it is exactly the same of going from 1 to 2, from 2 to 3, from 3 to 4. So if you are regressing sales directly on market concentration without any pre-treatment, what you are assuming is that these variables have a linear relationship. Basically saying, you know, very low concentration to low concentration has the same beta. Low to high, same beta. High to very high, same beta. And this is a very strong assumption. My advice to you here is that you want to leave your model more flexible, right? You want to leave that option more loose. And how can you do that? So the best way for you in dealing with those special controls, either categorical variables or ordinal variables, the best advice that I can give you is first create dummy variables for each one of those categories. All right, so if you have black, white, Native America, first create a dummy for black, a dummy for white, a dummy for Native American, or a dummy for no concentration, some concentration, high concentration. So this is going to allow you not to assume that you have this linear relationship. So let me just pause here because there is a big question coming from Brad. Brad is asking, are there indicators to test for endogeneity only in the first regression? We're gonna, I think we talked about that, or maybe I'm repeating myself. So we're going to look at some tests for that. Brad, remind me. Okay, sorry. Sometimes I forget if I answered. All right, so back to dummies. Best advice that I can give you is create dummies for those categories. If you do that, you're not assuming a linear relationship. You're leaving the model more flexible. Now, do I include every dummy variable in my regression? So let's imagine here that, you know, I give you the variable and you created your dummy variables, you generated your dummies, just the way you did in your homework. If you include every dummy, and you probably have seen that before if you take an econometrics, if you include all the possible categories, if you include all the dummies you created, you're going to end up with a problem that is called multicollinearity, right? So multicollinearity is basically saying if you know 4 of these 5 dummies, of course you're going to know the 5th one. Right? So basically, you can guess the value of one variable based on the other 4. And this is going to create a problem for the computer when running the calculations of your sample moment conditions, when running the estimations of your OLS. So to avoid multicollinearity, what you want to do is drop one category. So here in your example, you have 1, 2, 3, 4, 5 categories. What you want to do is include only 4 dummy variables, not 5. If you include 5, you're going to end up into the problem called dummy trap, right? Now, if you're running this in Stata, this is not going to be a problem because Stata will automatically drop one for you. Let's say you forget and you just simply put the 5 dummies there in your model. Stata will take care of that multicollinearity, will give you a message saying, hey, because of multicollinearity, I dropped one dummy variable. And this is not going to be a problem. It will continue on with the estimation. But just remember that that's something you need to be mindful, that you choose one dummy to be the baseline and you excluded this dummy from the model. So here in the green model, I'm excluding one of the dummies. The very low dummy is excluded, and so therefore it is considered to be my baseline, my base group against which I'm going to compare all the other categories. Okay, that's just something to be careful of. Okay. How to generate dummy variables on Stata? You can use the generate replace pair. That's something you can do, or you can use the more condensed version with just the generate command. Generate dummy high is going to be equal to 1 if market concentration is going to be equal to 3. Generate dummy low if market concentration is equal to 2. So before you even run your regression, the first thing you do is to just create those dummy variables. And this is going to leave you not assuming that you have a linear relationship. That's something more elegant, and that's something desirable for you to do. On Stata, remember that exclamation means not. So here, market concentration not equal to 0. Okay? All right. So when it comes to your project later on in the term, you don't have a final exam, but you do have a data project. That's nothing for you to be afraid of. I'll help you every time. I'm here. This is my job. But there's some guidelines for control selection, and this is something that I will be taking a look at when I'm grading your projects. How did you select your controls? What does the theory tell us about including those variables that are going to help us unbias our estimates, right? So the first thing is to think about your model. What does the theory tell us about including this variable or not? Variables that should be included because they theoretically affect your dependent variable, they should be in. Put them in no matter what. Right? If the theory tells you, gives you the background that this variable is important in understanding sales behavior, in understanding purchasing behavior, include them. What about the variables that could affect your outcome, right? That you're not so sure, theory is not so sure. So you want to include those variables and you want to run hypothesis tests. Then you want to check significance, right? So let's say you include this variable and immediately you look at the output, the variable is not significant. Don't be the advice here. So here's another advice for you. Some people are going to be too fast in just dismissing variables that are not significant. But be careful. Sometimes, even if you don't have individual significance, variables may work as a team. So remember these 5 dummies that we talked about? Sometimes you can run into a situation in which 2 of the dummies are going to be insignificant on their own, but together, when you conduct a global significance test, they matter, right? So joint significance is something that you want to be aware of before you just throw the variable away, okay? This is also disadvising against the kitchen sink approach that you learn in econometrics. Just throw everything in there, dismiss all the insignificant variables, throw them away. This is not how you do your models. If the variable should be there for a reason, even if this variable is insignificant, you may want to keep that variable because it theoretically is important for you that this variable belongs to the model, okay? So this is important when you are conducting your individual projects later on. How do I do a joint significant test? Juliana, you're talking about these dummy variables working as a team. How do I check if they are a team? Well, there is a command on Stata that is something that you guys learn, and it is called the test command, right? So basically you want to write the test, sorry, go back here. Basically you want to write test. You can, after you run your regression, you can write test and then variable 1, variable 2, all the way to as many variables as you want. Say you have all your dummy variables here for variable 4, And this test is going to test the hypothesis that they are all equal to 0. If you are able to reject this assumption, if you're able to reject the null, then they are jointly significant. They are statistically different from 0 as a team, okay?
Professor, this is Manishik. I have another question related to this. So if something is highly insignificant, for example, the p-value is 0.8, okay? However, theoretically, it has, or historically or conventionally, it has been shown or known to be important for the model. How do we decide whether to keep it or
keep it? Remove? Keep it. All of us, we still keep it. We don't throw away. We don't throw away. You're not fishing. You're not fishing for results. You're not letting the data guide you. The theory should guide you first. The theory comes first. If the theory tells you that, in that taxation should be there in your model, go ahead and include it, even if not significant. You will have a known result, but your model is better specified.
Okay,
thank you. All of us, we do leave it, all of us. So be very careful about throwing away things, right? That's my biggest advice here. Your book also talks about sanity checks. What is the idea behind sanity checks? Well, when you're pulling out those variables from your error term and you're bringing them up to your regression model, this allows you to have this just this reassurance step that you're getting something coherent, because most of the times those controls, they're going to have some expected signs. You expect, this coefficient on tax to be positive or negative, or this coefficient on income to be positive or negative, and this is just going to be a relief for you that you're heading in the right direction. So this is what we mean by a sanity check. They allow you to just, take a breath and continue on, making sure that you're not getting something crazy, stuff that doesn't look very weird from your regression output. The other thing that I talked about is the use of proxy variables. We're not going to spend much time here, but remember, a proxy variable is something that is serving as a surrogate for a control. So in some cases, it may be hard for you to include directly a control. How do I measure mindfulness, right? So usually we say we're going to proxy. We're going to proxy for mindfulness. We're going to proxy for CEO awareness in that way. And this is what a proxy variable is going to do. It must be a variable that is very much closely related to the variable that is being surrogated for, and it must be a variable that doesn't bring other endogeneity concerns, right? So that's the best choice for having a proxy variable that is going to approximate the control that you don't have. Now, this chapter concludes talking about the very first assumption. What about linearity? Does OLS model implies that we always should have this straight line that goes through our data points? The answer is no. How can we bend linearity? How can we modify linearity to be able to capture relationships between x's and y's that are intrinsically non-linear, right? So let's say, for instance, that you believe you have a relationship like that. So you have your x variable, and let's say this variable is education, right? Education. And sorry for my handwriting here, because I'm writing with my right hand and I'm left-handed. And you have wages. So sometimes you want to capture a relationship like that. So you want to have maybe this logarithm or quadratic type of relationship, this not straight line type of relationship, or maybe you believe the relationship is something that looks like that has some increasing returns and then fall back again. So how can I incorporate that in my linear regression model? You are still able to do so, because the assumption of linearity is just talking about linearity in the parameters, right? So one thing that you can have is that variable x can perfectly be a quadratic, can perfectly be a logarithm. What you cannot have is your beta being something to the square, or being something quadratic, or being something where you take the ln, right, the logarithm. So you definitely can have nonlinear curves, that's fine, and you're still having a linear regression model. So many students get confused about that, but just remember that linearity is linearity with respect to the parameters. So this model that you have right here is a linear regression model because it is linear in my parameters. When I talk about parameters, I'm talking about alpha, beta 1, and beta 2. It is okay to have quadratics, logarithms, whatever, cubics in your x variables. How do I interpret a model like that? What is this model telling me? So I have hours of training and then I have sales. What is this telling me? This is allowing me to be able to see, for instance, if sales go maybe up with hours of training, attains a maximum, and then falls back again. This is a quadratic function. And how do I capture that? I just include this extra term in my regression model. So if you choose to do that, there's little harm in attempting to change the functional form. You're always okay to try things. The worst that can happen is that you find that this term beta 2 is not significant, but you are, at least able to see if you have a relationship that goes like that, up and down, or goes like that, down and up. Okay, so you can have a concave type of relationship, up and down, or a convex type of relationship just by adding this quadratic term. Now, if you choose to add the quadratic term, you also need to remember to add the linear term. They gotta go together, right? And remember that we just talked about the joint significant test. That's a good opportunity to use it. Do they work together? So I can check whether beta 1 is significant, beta 2 is significant, and even if beta 2 is not significant, I could still check if they are together, something that matter. So by doing the test command hours square, right? So one important assumption of this model is that, instead of having sales and hours be something that change at a constant rate, so let's say you find beta is equal to 12. So you're saying if hours go up by 1 unit, sales go up by 12 units. So this is always something linear, something constant. And sometimes this is not just the nature of the variables. This is not just the nature of the relationship you want to capture. Sometimes you want to see, a non-constant effect. So here, how do I interpret beta 1 and beta 2? You cannot interpret them separately, okay? So if you ever, I think in the next homework, you'll have an exercise like that. So don't go ahead and interpret beta 1 and then beta 2. The way you're gonna interpret that is taking the first derivative. So what is the effect of hours on sales? This effect is gonna be beta 1 plus 2 beta 2 times hours. Okay, so now we don't have a constant effect anymore, but we have something that changes with the level. Now the effect depends on how many hours we are at. And this is something richer. This is something more nuanced about the data. Now, if beta 2 is negative, remember from your math in the past, so if beta 2 is negative, you have this relationship over here. This is beta 2 less than 0. You're going to have a concave type of relationship. So let's say when you get older, your income increases, your income reaches a certain maximum point, and then your income falls. Here, the opposite, right? So beta 2 is greater than 0. You have a convex function. So the interpretation, you got to be careful. When you change the functional form, all you need to be mindful of is really how to interpret those betas. They got to go together. They cannot be separate anymore. Okay? How do I generate those variables in Stata? With the generate command. So let's say I want to estimate this model here. This is something you're going to be doing in your homework. So you can do generate price square however you're gonna call, I'm gonna call price2 equals price squared, okay? So now you can run the regression, sales on price squared. You can go ahead and do this model. Here, what do we see? We have a significant price, but we have a non-significant price too. How do I test globally if they're working as a team? Test price2. We just went over these commands, right? So here I'm gonna reject, my p-value is 0, so I'm gonna reject the null, and therefore they matter as a team, okay? I can go ahead and upload those commands for you. What else? Just to finish off, well, sometimes instead of quadratics, we may also have logarithm versions of your y's and x. That's perfectly okay. Some of you in your project may end up with a variable that is measured in logarithm terms, right? And all they are trying to do, once again, is capturing non-linearities, okay? So you may have a model in which you take the log of your dependent variable and you regress on your x variable. So we call this model log level model. That's one version. Just as we had quadratics, we can have the log level. It is still a linear regression model. So this model is basically, if you want to think about it, you know, geometrically, this model is something like that. Okay, so if you want to think about the functional form. Now, how do I interpret my beta? How do I interpret this number over here? Be careful. If you have the logarithm on your y variable, you want to memorize that, or you can go over the mathematical proof. I'm not going to go over the mathematical proof here. But the way I read my beta is, if I increase my price in 1 unit, my sales are going to change by 100 times beta %. So if I increase my price in 1 unit, I'm going to change sales by 5%. So instead of having levels, now we have percentages. And sometimes economists and financists, they like to think about models like that. The other thing is true, if you have a level log model, again, memorize those interpretations. I really advise you to do that. How do I interpret the coefficient if now you have ln on your x variable? And here is something that has kind of this shape over there. So you have this increasing, but it returns, but at a decreasing rate, right? So capital goes up, return on capital go up at a decreasing rate. So that could be a model suitable for returns to capital, at least in the short run. So here, how do I interpret this coefficient? A 1% increase in x, it's going to change my y variable by beta over 100 units. Be careful if you ever have these logs. That's something you want to be careful when you're interpreting. Finally, the most common type of model, I think many of you will have that in your project, the log-log. The log-log model, you take the log on the right-hand side and you take the log of your treatment variable, left and right. So here, log of sales, log of price. This is the most common model for economists. Why that is? This is a demand function, right? So sales and prices. How do I interpret this beta over here? What is the interpretation of 0.35? If I increase my price in 1%, my quantity is going to increase. There should be a negative sign. My quantity is going to decrease, law of the demand. My quantity is going to decrease by 0. So here should be a decrease by 0.35%. So we have a percent against percent. And if you have taken a microeconomics course, you probably know that this beta right here is something that economists is going to call elasticity, the price elasticity. So how sensitive is your sales to your prices in percentage terms? If I change my price in 1%, what is the expected change in your sales? And in this case, it's 0.35%. If you ever taken a micro course, you're going to say this is a very inelastic product, right? So consumers here are highly dependent on your product. If you have an economic crisis, this demand is not going to fluctuate a lot. You can think about necessities, you can think about medicine for your heart, things like that. Okay, so for this last part, remember the interpretation changes when you are logarithmizing on the left and on the right. And you're still not violating linearity whatsoever. You still have a linear regression model for sure. Okay? And that's concluding this chapter that talks about so many things. Selectivity, when is a problem? We talked about that when we're selecting according to a Y variable. Endogeneity, biggest enemy that we have as analysts. How do we deal with that? We talked about two strategies, controls and proxies. Next week, we're going to talk about a more advanced one. And functional forms, they are very flexible. They still do not violate linearity. The only thing you need to be careful is how you interpret, and I give you this table of how you can interpret them, okay? And this is basically what chapter 7 talks about. Any questions before we conclude? I already posted homework 3. This is going to be due on Sunday, and the very Sunday before the week of the 4th of July. And this is going to be on chapter 7 and next week's material. Okay? Any questions before we conclude? No? So if there are no questions, thank you very much for joining me. And please feel free to reach out by emails. I'm here to help you anytime. This is my job. Thank you so much. You guys have a wonderful night with your families and friends. Thank you. Bye-bye.
Thank you, Professor.
Thank you.